I think. Our next speaker is Alan Prusinowski from Ohio State University. So he's a student that's working in David Nagib's group. So at this stage, I'd like to open it up for David to introduce Alan.
Hello, everybody. Can you hear me?
Yes.
Thumbs up. All right, time for a nice stretch midway. So it's my pleasure to introduce Alan. He is a fourth year after, I guess, one more defense in the group. He'll be the senior-most student in the lab. He comes from upstate New York, way, way, way upstate. The type of place where people from there like to tell you what lake they're from. So Alan can tell us what lake he's from later. But so he went to undergrad at Lemoyne College near Syracuse. And in my group, a couple of things I could tell you about, but maybe the most recent accomplishment he's done, he entered a university-wide competition across all of Ohio State, and he emerged as one of the top 5 scientists presenting his work. And so that'll actually be the presentation he presents right now. And I'll just say it's a pleasure to work with Alan. He's very thoughtful, and I'm sure that might come across in this presentation. Take it away, Alan.
All right, thank you, David, for that introduction. So I'm really excited to have the chance to present to all of you today and my live audience of my cats from my apartment. My work is centered on functionalizing multiple aliphatic CH bonds in one operation. And today I'll share our work in leveraging a radical polar crossover manifold to achieve vicinal difunctionalization of alcohols. So I don't think I have to convince anyone here that CH functionalization is difficult and it's a highly valuable way of diversifying molecular scaffolds. But when we think about this in the realm of radical reactivity and aliphatic CH bonds, we can really appreciate the challenges of achieving a site-selective functionalization. For example, in the CH chlorination reaction that we teach to undergrads, the reaction is essentially non-selective, giving a one.
Can I interrupt you? I assume you want to be sharing screen, yeah? You want to be sharing slides.
Yes, let's see.
So you go to the share screen.
Is that up now?
No, not yet. So you click the share. Rio, do you want to be the driver?
Sure. Yeah. So if you, there we go.
Perfect. You're such a great driver, Rio. It's amazing. Fantastic.
Did that help? All right. So when we think about this in the realm of functionalizing alcohols through radical manifolds, we can think about breaking these CH bonds into their corresponding radicals and replacing it with a new functional group. But again, selectivity is challenging due to these relatively high energetic barriers and the similar bond strengths. But we've come up with a pretty clever way around this challenge, and we call that radical relay chaperones. So in this strategy, you select the hydrogen atom that you want to replace and the group you want to put in its position. So first you attach your chaperone, and what's important about the chaperone is that you can generate a radical on it. So this radical species can undergo a hydrogen atom transfer. And in this talk, I'm going to focus on 1,5 hydrogen atom transfer. So following a radical relay, you're able to generate a carbon-centered radical in place of that hydrogen atom. You can trap your new group and remove the chaperone to get to your functionalized alcohol. And we've had quite a bit of luck in implementing this strategy, particularly in Imidate chaperones. So in the Imidate chaperones, you start with an alcohol, you append a nitrile to get to your Imidate. Through an electrophilic halogen, we're able to generate our Imidate radical, which undergoes a hydrogen atom transfer to get to this directed carbon radical. So this is our key reactive intermediate. So to give you a quick flavor of the transformations we can achieve, we've been able to perform a CH amination, this double CH geminal functionalization where we can get to either 2 of the same halide or mixed halides. We can also undergo this tandem functionalization where you first aminate and then oxidize to get to oxazoles. And the story that I'm going to focus on today is going to be how we've been able to develop a vicinal di-CH functionalization. I'm going to try to convince you just really how powerful this transformation is. So from our previous work, we learned that combination of iodine and iodobenzene diacetate forms acetyl hypoiodate. And when reacted with an imidate, we make this really weak Ni bond, which is photolized to give the nitrogen-centered radical. we can then undergo our hydrogen atom transfer, trap a halogen to get to this alkyl iodide. And we thought that this could undergo an elimination reaction to get to an alkene, and then through an iodocyclization, we could get to these iodoaminated products. And this was really attractive to us because we could imagine diversifying these molecules even further to get to things like serenol and aminoserenol, and just really rapidly increasing the complexity of simple molecules. So we thought this would be feasible based on work out of the Barluenga group showing that alkyl iodide elimination can occur through a polar mechanism in the presence of a hypervalent iodine. And in this process, first you undergo a CH iodination and then a desaturation, which presumably undergoes this lambda-3 iodine intermediate. Following elimination, you can go through this iodoacetoxylation. And a really key piece of data here is that under thermal conditions and photochemical conditions, two different products were observed. So under photochemical conditions, they seem to stop at this alkyl iodide, but under thermal conditions, they undergo elimination and to this iodoacetate. So this gave us confidence that we could achieve the key elimination step of this mechanism and diverge our reactivity. So we started off with this trichloroacetimidate. These are incredibly easy to synthesize, and we use iodobenzene diacetate and molecular iodine in the presence of visible light. We were trying to get to this difunctionalized product, but we were well aware that the CH amination and CH halogenation was also a possible pathway. So we saw an incredible solvent effect in this reaction where nonpolar solvents like toluene gave us the CH halogenation reaction. Switching to HFIP as the solvent, we actually see complete selectivity for the CH amination reaction. And we were really excited by this result with terbutanol. So we recently were asked what our favorite solvent was, and I heard terbutanol, so that made me pretty excited because that's also our favorite solvent in this reaction. It gives us almost complete selectivity for our desired product. So the energy source is pretty important for this reaction. Using LEDs are inferior to using just simple household light bulbs. And then the halogen source, we saw that iodine sources were superior to other halogens. But what's really important to notice here is that between sodium iodide and molecular iodine, we see completely different diastereomeric ratios where I2 is far superior. So we wanted to look at this a little bit more. And the key observation here was with I2, you have a really high concentration of molecular iodine, and that correlated to a high DR. So when we're looking in the vials, at the end of the reaction, this is very fast. In about 30 minutes, it's complete. There were still a couple I2 crystals in the bottom. So we thought that we could fully solubilize all of the iodine by putting a pre-stir at the beginning of our reaction. And when we do that, we were really happy to see that we drastically increased the DR of this reaction to 19:1. So using this strategy, we were able to generate a wide range of oxazolines where the nitrogen is connected to a tertiary carbon. Particularly to note are these 4-membered rings that work well in this reaction. We can also tolerate ethers, tosylamides, and esters. And secondary alcohols work well in this transformation. When we go to acyclic alcohols, we can generate primary alkyl iodides. And a really interesting result is when you have a competition between these two possible pathways, we see an 8:1 regioisomeric ratio toward the internal product. And when you amp up the acidity of that internal proton, you see almost complete regioselectivity. So noting the value of the spirocyclic oxazolines, we really set out to demonstrate that a wide range of nitriles could also be used in our reaction, including a variety of para-substituted benzonitriles from electron donating to electron withdrawing. Meta substitutions fused by aryls and alkyl nitriles also work really well in this reaction. So we next turn to probing the mechanism of our transformation. So as I showed you before, starting with our imidate, acetyl hypoiodite can get us to this carbon-centered radical, and we trap that to get to the alkyl iodide. So we imagine two possible pathways here for the elimination. The first would be direct elimination of the alkyl iodide to generate the olefin. And the second involved an I2 complexation. So we believe that this was the pathway based on some data that I'll show in the next slide. Once we get to this hypernucleofuge, we think this can eliminate to get you to an alloimidate, which again has a choice to go under two pathways. The first being a single electron pathway where you can oxidize the nitrogen and undergo 5-exotrig cyclization. and the second being an iodonium formation followed by a cyclization and ring opening. So we're able to validate intermediates by independently synthesizing them. So excitingly, this tertiary iodide gives us our product in great yield, as well as this alkene. But we did get another piece of information from this allo-imidate, and that was when we changed the solvent to dichloromethane, we saw a decrease in the diastereomeric ratio. We were able to resurrect that by putting a radical trap such as tempo into the reaction. We believe that's because we're suppressing a radical cyclization pathway, leading us to favor the polar cyclization, which leads to a high DR. So we did look at alternate pathways, including a beta fragmentation induced desaturation, as well as a non-directed reaction in which this tertiary alkyl, this tertiary CH bond was abstracted by a radical in solution. And in both experiments, we saw no reaction and complete conservation of our starting material. But unexpectedly, KIE data shows that HAT is not the rate determining step of this mechanism. And this was interesting because in our previous reports, such as the CH amination reaction, HAT was the rate determining step. And what we also learned from this is that the rate determining step occurs after the hydrogen atom transfer. So we were really interested in how this elimination occurs. From the literature, we first hypothesized that we were going through this lambda-3 iodine. However, when we subject the alkyl iodide to oxidant, we see 0% conversion. So we don't believe that this is actually the intermediate in our reaction. But an interesting result was when molecular iodine was stirred with that alkyl iodide, you see 100% conversion of that intermediate. So we hypothesized that rather than going through a lambda-3 iodine, iodine is acting as a Lewis acid, and we're getting to this complex where a tertiary alkyl iodide will form a more favorable complex than a secondary alkyl iodide. And this, in fact, plays out in our reaction because we have a reactive tertiary alkyl iodide intermediate, and our products are secondary alkyl iodides, and those are rather stable to our conditions. So I showed you that our reaction works to generate oxazolines at a tertiary site. And we really had some challenges accessing secondary CH bonds. So we had to get pretty creative with this one. And the reason is that that I2 complexation event is less favorable in the case of secondary alkyl iodides. And we're able to get around this through different strategies. The first is leveraging the beta silicon effect to enhance the elimination of that iodide, getting us to this primary alkyl iodide in great yield. We were also able to get around this by enhancing the acidity of this proton, and we were able to do that in the case of ketones and esters. And finally, when we get to the secondary alkyl iodide next to an isopropyl group, we believe we're going through a strain-induced elimination to get us to this final product. So I showed you that we can use our protocol to generate these iodoxazolines, and I really want to show how versatile this product is. So we can think about it in a variety of different ways. The first is breaking the CI bond. So we can undergo nucleophilic substitution and get to a wide variety of products, including nitrogen addition, oxygen, and this biotinylation. When we tried to substitute the alkyl iodide with a thiol, we saw a really interesting result where we not only substituted the alkyl iodide with a thiol, but also one of the chlorines of the trichloromethyl group, followed by a reduction of that dichloromethylene. We're also able to get to a series of aziridines using our protocol. The other bond that you should be excited about in oxazolines is the CO bond. And using acidic conditions, you're able to add halogens in the place, or we can get to these amino alcohols. So we're really happy with the transformation we were able to achieve, but we really wanted to challenge ourselves a little bit more and try to streamline this protocol to go directly from alcohol to the iodohydroxylamine in just one operation. And really the challenge here is that alcohols are readily oxidized under the reaction conditions. So to avoid this, we pre-installed our chaperone in all of these cases, and then we subjected the imidate to the conditions. So if we want to achieve this telescope method, we have to outcompete side oxidation. And we thought we might be able to do this by affecting the rate of alcohol oxidation by changing solvents. And it turns out our first idea wasn't very good. we noticed in a variety of solvents, I'm just showing two here, trifluorotoluene and terbutanol, that the rate of oxidation is essentially the same, where we're seeing the consumption of alcohol over time. But what we were excited by is actually the rate of imidate formation is very different in these solvents. So in trifluorotoluene, you see an enhanced rate of imidate formation as compared to terbutanol. And this plays out in our reaction when we subject alcohol to chaperone oxidant at the same time. After 24 hours, we see only 20% in the case of terbutanol and 75% in the case of trifluorotoluene. And we've been able to show this on a variety of alcohols, and using X-ray crystallography, we've been able to show the trans stereochemistry of our products. So hopefully today I've been able to convince you guys that we've come up with a pretty good way of performing vicinal CH functionalization of alcohols, and we've gone to a pretty wide range of interesting molecules using this protocol. And of course, chemistry is a team sport, so I'd like to thank first David Nagib and the entire Nagib lab, and Ethan Wappis and Raymond Tremacy, who worked with me very intimately in this project. Thank you for the invitation, and I'd be happy to answer any questions you guys have.
Hey, Alan. This is Alex from the Montgomery lab. I have a question for you. I was wondering if you guys have tried doing this in an intermolecular fashion. So if you have your chloroacetamidate on maybe, I guess, like a shorter alcohol, could you do it in an intermolecular fashion?
We have looked at intermolecular reactions using our imidates. Most of the success comes on benzoic sites, but we haven't yet pursued that.
Awesome, thank you.
Any other questions? So I don't have a question, but a general comment. Yeah, that's really very elegant, the way the group continues to develop new angles to the Hoffmann-Lafleur Freytag type reactions. It's amazing the range of clever applications you've achieved. So congratulations very much indeed. Okay, well done.